4 weeks remain until the sky lights up to welcome the year 2026. Millions of fireworks sit ready in storage, waiting to ignite that specific moment. One can notice how the dark casings betray nothing of the brilliant explosions hidden inside. But this is just the beginning. Have you ever wondered how many intricate steps are required to create these fleeting bursts? The pyrotechnic display itself lasts only a few seconds. But in reality, behind every burst of light lies an entire craft-driven journey requiring absolute precision. It is visible how the production moves from chemical mixing rooms to the specialized star-forming lines. Tightly controlled assembly areas pack the components into shells with calculated care. The camera glides past ingredients that seem almost lifeless, yet hold the potential for massive energy. Everything only gets more complicated. Thus, the silent world of production prepares the beauty that lights up the night. A few dozen degrees separate a perfect burst from a complete failure. Blue remains one of the rarest colors to ever appear in the sky. To create it, copper compounds must burn within an extremely narrow temperature window. A slight deviation shifts the hue toward an unwanted green or a washed-out white. But this is just the beginning. Manual labor remains essential for the process. Why does modern production still rely heavily on hand craftsmanship? In the age of automation, mixing by machine seems faster. Yet, skilled artisans must personally mix, press, and dry each individual star. One can notice how the material takes precise form under their tools. At first glance, the work looks peaceful, but behind the beauty lies a silent layer of risk. Coloring agents like barium or copper are harmful if inhaled over long periods. Consequently, workers operate in short shifts using full protective gear. Industrial air filtration systems run continuously to purify the workspace. The cycle continues in a strictly controlled environment, thousands of times. That is exactly how often color formulas undergo testing before entering the production line. Behind every brilliant burst of fireworks in the sky lies a chemical mixture prepared with near-perfect precision inside an isolated mixing room. Technicians meticulously weigh ultrafine charcoal powder to strictly set the burn rate, while sulfur is added to keep the reaction stable throughout the process. Potassium nitrate acts as the essential oxidizer that allows the mixture to ignite at exactly the right moment. But this is just the beginning. Why is the mixture passed through steel sieves with such an extremely fine mesh? The powder already contains highly purified metal salts, such as strontium for red, barium for green, sodium for yellow, and copper nitrate for the rare blue tone. However, the smooth powder must fall through like a continuous stream of black sand, while any clumps or oversized particles remain trapped on top. This step brings every grain to a consistent size, which is a crucial requirement to prevent hot spots that could distort the color or destabilize the burn. One can notice how the sifted ingredients are loaded into large steel drums for the final blending stage. At first glance, the rotation of these drums seems like a simple mechanical action, but in reality, it guarantees that every particle coats and binds evenly with the others. The drums rotate slowly for hours to create a fully uniform, safely refined powder. This mixture becomes the heart of the tiny pyrotechnic stars that will eventually light up the darkness. The process is only gaining momentum. Once the powder reaches the proper fineness, it transfers to the pressing area where specialized hydraulic machines wait to compress it. Technicians load the material into multi-cavity metal molds, where each cavity forms a raw, cylindrical pellet significantly larger than the final burning grain. The press descends with the heavy hum of hydraulics and holds pressure for 3 to 5 seconds. This duration ensures each pellet achieves a stable density, neither too porous to crumble during combustion, nor too hard to hinder later shaping. It is visible how the mold opens to reveal rows of dark, matte pellets packed tightly across its surface. Workers gently tilt the heavy mold, allowing the pellets to slide onto wooden trays lined with anti-static paper to further reduce any spark risk during transport. These trays travel to multi-tier racks inside a temperature and humidity-controlled room, awaiting the next phase. Transition to the next level. The raw pellets must now enter a rotating drum to stabilize their surface and increase durability. These drums are typically made of stainless steel and positioned at a 30 to 45 degree angle to ensure optimal tumbling. Technicians load an appropriate amount of pellets inside and switch on the slow rotation mode. As the drum turns, they spray a thin binder solution or dust on additional dry powder, depending on the specific technical requirements. One can notice how the binder gradually strengthens the outer layer, preventing each pellet from chipping during handling. If a larger grain size is required, the process becomes more intricate. Technicians alternate between spraying binder and adding powder through multiple cycles, increasing the diameter by only a tiny amount with each pass. The drum's rotation speed remains intentionally low to avoid excessive friction while allowing the coating to spread evenly. Basic rounding may require only 20 to 40 minutes, but for layered growth used in aerial display shells, the process extends to 2 or 3 hours. From here, the rounded stars move into the drying stage to stabilize their structure. Technicians spread the stars into a thin, even layer across wide trays, ensuring each piece has enough space so they do not stick together. In modern factories, drying takes place indoors at temperatures between 77 degrees Fahrenheit and 86 degrees Fahrenheit. Humidity is kept stable, so the binder layer dries slowly without cracking. In contrast, traditional workshops or large-scale operations in parts of Asia use a different approach. Stars dry under direct sunlight, but always remain beneath an open-sided canopy to prevent rain exposure. This shield protects the stars from overly harsh sunlight that could cause the moisture to evaporate too quickly. Throughout the drying period, workers rotate or reposition the trays so every star receives an even amount of heat and airflow. The total drying time ranges from several hours to more than 1 full day. Finally, the production line splits into 2 separate paths for tube-style fireworks and aerial shells. Multiple layers of rolled craft paper or composite materials stand ready to withstand the high pressure generated at the moment of ignition. These cylindrical housings determine how the visual effect will appear once launched into the sky. After the stars reach their proper dryness level, technicians move the combustible pellets into the firework tube using a funnel or a wooden scoop. One can notice how they guide the material gently, strictly avoiding any hard impact that could damage the sensitive chemical composition. But this is just the beginning of the assembly process. Why is the amount of stars placed inside each tube calculated by a specific formula? A deviation would alter the visual output completely. Fewer stars create a single, sharp streak of light, while a higher count produces a denser, more vibrant burst in the night sky. Therefore, every production batch maintains consistent star quantity to prevent noticeable variations during rapid-fire sequences. The tube's opening is cleaned and inspected to ensure all stars sit correctly without tilting or touching the inner walls. Black powder in a coarse grain form acts as the propellant that drives the assembly upward. Why use this specific grain size for the lift charge? At first glance, it seems any explosive powder would suffice for launch. But in reality, the specific burn rate of coarse grains provides the precise thrust needed, unlike the fine powder used for mixing stars. Technicians measure the charge according to a fixed specification because even a few extra grams or a few grams too little can directly affect the height the stars are able to reach. It is visible how the powder pours into the tube through a funnel, settling beneath the stars. A wooden or plastic tamping tool is used to secure the lift charge without damaging the pyrotechnic payload above it. Once this layer is properly compacted, technicians verify the total height inside to ensure the distance between the stars and the lift charge matches the intended design, guaranteeing the correct trajectory. The process is only gaining momentum. Attaching the fuse dictates exactly when the firework activates, requiring more caution than almost any other part of the assembly line. It looks outwardly simple to insert a fuse, but in reality, this component controls the critical ignition timing for the entire display. Each firework tube is brought to the mounting station where technicians cut the material to a standard length. There are two main types: a slow-burning fuse that creates a delay, and a fast-burning fuse used for rapid fire or sequential effects. One can observe how the end of the fuse is inserted into the mouth of the tube and fixed in place with a craft paper wrap or a specialized adhesive. Finally, the tube opening is sealed with a pressed paper cap or a thin plastic cover to protect the interior from moisture and to ensure the stars remain firmly in position. Two hemispherical paper casings form the structural foundation of the complex aerial shell. Unlike the simpler tube-style fireworks, this production line requires molded forms made from compressed pulp or multiple layers of craft paper to withstand the initial explosion. Technicians take the fully dried stars and prepare them for precise placement inside these hardened shells. At this stage, the time fuse has already been installed at the center of the hemisphere. But this is just the beginning. Workers arrange the stars in strict concentric rings around the central fuse. Why is the specific layout of these small pellets so critical? To the untrained eye, it looks like a simple filling process. This ring-based arrangement guarantees that the explosion results in a perfectly rounded flowering pattern across the night sky. One can notice how technicians carefully inspect the spacing between every individual star to ensure absolutely no contact exists between them. This prevents off-center burning or premature ignition during the flight. Each factory utilizes its own method, creating a single ring for a simple burst or up to 3 rings for a denser visual effect. Specialized patterns like hearts, rings, or chrysanthemums require even more complex positioning. It gets more complex further on. Because the stars cannot disperse without propulsion, a burst charge is introduced into the cavity. At first glance, mixing black powder with rice hulls seems like a simple volume filler, but in reality, the hulls play a critical structural role. They create necessary porosity, helping to distribute the explosive force evenly during the detonation. The hulls are pre-soaked in explosive powder before being poured into the space between the layers of stars. Technicians fill the central space completely without packing it too tightly. Therefore, the density of this layer determines the success of the firework. If it is too loose, the shell bursts weakly with a sparse effect, while too much compaction causes internal pressure to rise dangerously. Everything only gets more complicated. The process moves to joining the two hemispheres into a single spherical shell. Immediately after aligning the halves, technicians apply a ring of adhesive around the base of the time fuse. They wrap it tightly with craft paper string to seal the fuse entry point, creating a solid airtight joint that prevents gas leakage. Then, they reinforce the entire seam using paper glue or a starch-based paste to ensure integrity. Multiple layers of craft paper are wrapped around the shell to increase its structural strength. It is visible how the number of layers increases depending on the shell size, with 3-inch shells requiring only a few wraps, while 6-inch to 8-inch variants demand many more. One can notice how the surface is pressed gently to preserve the perfect spherical shape during application. Technicians smooth every sheet firmly to ensure there are no trapped air pockets that could destabilize the flight path. The production phase ends here. Inspectors perform essential measurements on the weight of each shell and the thickness of the paper layers. They verify the airtightness of the casing, the condition of the fuse, and the placement of the lift charge. Because external checks are not enough, the factory selects several shells from each batch for live testing. These samples are brought to a dedicated range and placed inside a steel test mortar equipped with high-speed cameras and pressure sensors. The goal is to verify 3 key parameters: the exact timing of the fuse, the altitude the shell reaches, and the spread pattern of the burst charge. And this is not the limit. Once inspection standards are met, the batch moves to the packing area. Workers sort each firework according to its diameter, effect type, and batch number before sealing the cartons. The packages are transferred to a separate storage zone where temperature and humidity are continuously controlled to prevent moisture absorption. From this point, the fireworks are loaded into specialized shipping containers for delivery to professional operators. Thousands of completed units are dispatched to ports or professional fireworks operators. Why does the process require such intense scrutiny? The assembly line seems consistent, but without strict control, the black powder could behave unpredictably. From tiny grains to brilliant bursts, the journey is shaped by precision and generations of craftsmanship. One can notice how shells are secured. Engineers oversee hours of mixing, pressing, shaping, and sealing the internal stars. It is visible how the composition texture changes under hydraulic pressure. Testing confirms the stability of the mixture. But this is just the beginning. At first glance, pasting the shell looks like simple wrapping, but in reality, it determines the symmetry of the explosion. Every shell that rises into the air carries these layers of structural integrity. One can notice the binding agents soaking the paper. It gets more complex further on, because countless quiet steps must be perfect long before a single spark is ever lit. Consequently, the phenomenon is engineering pushed to its physical limits. Artisans turn raw materials into technical art. The product is ready for the final stage of its life cycle.